Dr. Milano, you there? Dr. Milano?
Yes. Yeah.
So let me introduce you to my professor, supervisor, Professor S.A. Hussain. Please.
Nice to meet you.
Yeah, hello. Good
Hello.
morning,
Nice.
Dr. Milano. Yeah, I
Good
welcome
afternoon.
you here. Yeah. So it's nice that we will have some kind of interactions.
So we shall start the program at exactly 3:30 p.m., sir.
Okay.
Okay.
Yeah, that's good.
Okay.
Hello, Dr. Milano. Am I audible to you?
Hello?
Am I audible to you?
Sorry?
Am I audible to you?
Yeah, I can hear you. When do you want, I can share my screen.
Okay, let's do it. So good morning, Dr. Gianluca Milano, and good afternoon, everyone present here. This is Shazidul Hussain, Research Scholar, Department of Physics, Tripura University, India. Today, we all gathered here to be a part of a research interaction with a young researchers from Italy, Dr. Gianluca Milano. It's my pleasure to welcome you all, our professors and other research scholars and master students in this second edition of Research Alaap program. Now, I would like to request our Professor S.A. Hussain, Head of the Department of Physics, Tripura University, to kindly present his welcome address. Sir.
Yeah. So, first of all, good afternoon to today's speaker, Professor Gianluca Milano, and my dear students and my colleagues who are present over here. On behalf of the Department of Physics, Tripura University, and also on behalf of my research group, Thin Films and Nanoscience Research Group, Department of Physics, Tripura University, I welcome you all to this interaction program. Specifically, I welcome Dr. Milano because he has agreed to discuss with us and about his work as well as our work. There will be an exchange kind of interaction. So I am very happy to welcome you, Dr. Milano. In the Department of Physics, Tripura University, we have 4 research groups working in 4 different areas. Specifically, one group is working on theoretical condensed matter physics, another group on atmospheric science, and another group on nanomaterials and nanoscience, and my group are working on thin films and nanoscience, and specifically we work on designing organ memory for raw. Biomaterial as well as plant extracts to design biodegradable and apply them to design colorimetric sensors. We try to design some nonlinear optically active material also to apply them on optoelectronics devices, and also we try to study different orders of nanoscale aggregates in thin films so that we can apply them on optoelectronic devices. So this is a small brief introduction about my lab, and at present 6 scholars are working in my lab, and already 10 PhD students awarded and they are graduated from this lab. Also several MPhil and MSc students also trained in the lab. With this, I welcome Dr. Milano once again, and hope this interaction will be fruitful and we shall be able to continue, and there will be some positive outcomes from these interactions, and hope all the participants, specifically our students, will be benefited from these interactions. Thank you very much, Dr. Milano, and also Ritanaba, for your effort to arrange these programs. With this, I conclude my welcome address. Thank you very much.
Thank you very much. Thank you very much for sharing your ideas and for sharing your capabilities.
Thank you, S.A. sir, for kind words. So this is Research Alaap. Alaap means conversation, where our interest is to know the research norms and the efforts made by global scientific community in the field of research and development. We thank Dr. Gianluca Milano for his sincere gratitude to become a part of our Alaap that is conversations. Now a brief introduction about Dr. Gianluca Milano will be given by Mr. Ritinabo Banik.
Thank you. Thank you, Sajidul. Dr. Milano, is that okay for you? Can you hear me?
Yes.
Yes. Okay. Okay. So in this edition of Researchers Alaap, we have with us Dr. Milano. Dr. Gianluca Milano is currently permanent researcher at the Italian National Institute of Metrological Research, INRIM. He received his bachelor's and master's degree in physics from University of Torino in 2013 and 2015 respectively, working on the growth and characterization of graphene. Then he obtained a PhD in physics cum laude in 2019 from Politecnico of Torino, working in collaboration with IIT and INRIM on Memristive Devices based on nanostructured materials. During PhD, he spent a visiting period at RWTH Aachen University, Germany. His main research interests and activities focus on the investigation of electronic and ionic transport properties and physicochemical phenomena in nano devices and low-dimensional systems. Memristive devices and architectures of memory and neuromorphic applications, from material synthesis to device characterization, modeling, and implementation of unconventional and brain-inspired computer paradigms. With this note, I welcome Dr. Milano. You can please proceed, sir.
Thank you very much for your welcome introduction. I hear my voice again. So maybe it's a problem of... Can you please deactivate your audio?
Okay, let me check.
Okay, because I hear you back. In the meanwhile, I would... Okay, now I think it's fully okay. I will try to share my screen. Can you see my presentation?
Yes.
Thank you very much.
Okay, you can carry on.
Thank you. So first of all, thank you all for inviting me to give this talk. It's always a pleasure to share our results and so our main research activities in our labs. So the title of this talk is Memristive Devices from Fundamentals to Neuromorphic Computing. So the idea of this talk is to share some ideas on how we do research, how are our capabilities and our main interests of our labs, and also the main results that we have obtained during last few years, I would say, without going into much detail. So if you want to know more details about some parts of this my presentation, please send me an email or write me. Okay. So just a few words about the Italian National Institute of Metrological Research. So we are the National Metrology Institute of Italy, and we are located in Torino. And this is a public research center under the jurisdiction of the Ministry of University and Research. And this campus, that is a very large campus with more than 80 laboratories, is devoted to the study of science of measurement and to research into materials. These are the main research objectives of this research institute. And also, this institute realized the primary standards for the basic and derived units of the International System of Units. So these ensure the maintenance of such standards and also the international comparison, providing the national measurement traceability of the system of unit. So basically, this is a research center devoted to a wide range of physical interest. And in particular, I belong to this group that is called Nanoscience, Nanoscale Science and Technology. And we are 12 researchers, 1 technician, actually 1 postdoc and 7 PhD students. And so we work on different topics ranging from micro and nanoelectronic devices for a wide range of applications that include sensing, metrology, but also neuromorphic devices, as I will talk later. Then a 3D model system for reference materials and standards, and also to, in general, to the nanoscale manipulation of objects and matter. And so we deal with advanced materials such as deep block copolymers, metamaterials, and metal surfaces, 2D materials, and so on. So these are just few pictures of the nano world in our labs. So the main lab of our group is includes both the fabrication of thin film and devices, that includes deposition, etching, patterning, and characterization of nanomaterials, and also all the tools required for lithography. So we have a clean room, ISO 5 clean room, and ISO 5 lab for the deposition of thin film materials. We have a so-called plasma lab for deposition and etching. And then we have a semiconductor lab with rapid thermal annealing, MBE growth, and we have a nano facility that includes electron and ion beam tools for both lithography and characterization of nanomaterials. So just going more in details about the nano facility, this is a laboratory dedicated to nanofabrication by ion and electron beams that includes a dual beam quanta 3D instruments and an expect SEM that allows both to characterize the materials and to thanks to the nanopattern generation system, also to perform electron beam lithography and to perform ion beam, focus ion beam, patterning, and deposition of conductive materials through ion beam induced deposition. So this is the idea, the main idea of our lab is to explore all the ranges of lithography, going from conventional lithography with optical and laser lithography, from centimeter scales to the micrometer scale, I would say. Then we have electron beam lithography that can pattern objects in between 500 nanometer and 50 nanometer. And then we have, besides conventional lithography, we have self-assembly as an alternative to conventional lithography that includes the nanosphere lithography, that can go down to 80 nanometer scale to pattern substrate on large area, as well as the use of block copolymers that can allow lithography down to 10 nanometer. So we have a fabrication capability and patterning that spans a wide range of resolutions from few centimeters down to the nanometer scale, even on large area. And with this, we can perform patterning on films, surfaces, and devices in general. So in order to understand one of my research topic that is related to memristive devices, I would like to give you a short background about the race towards future computing. So why we need to develop new devices. So because we are racing towards the future computing, and the obstacle now towards future computing is the Moore's law that is related to the physical limits of further transistor scaling. So I will not go into details because I think most of you already know about the end of the Moore law. Then the second obstacle is the so-called heat wall. So related to the reduction of transistors that are actually the main devices for the realization of computing architecture, the reduction of this transistor leads to an increased leakage electrical current that is related to an increased Joule heating. And this further limits the transistor scaling due to Joule heating effects of the chip with consequent breakdown. So together with the Moore law, this obstacle, the race toward future computing architecture, and also the third obstacle is the so-called memory wall. So if we think about a computer now, for most of the application, the 96% of the execution time is related to the access of memory. So it's related basically to the exchange of data in between memory and CPU, and only 4% of the execution time is related to computing. And this is the so-called von Neumann bottleneck that is related to the architecture based on the distinction in between memory and processing of the information in between RAM and CPU. And so, as a consequence, new computing paradigms are gaining new interest in the research community. This includes the new generation memory storage, but also and mainly bio-inspired computing and in-memory computing. All these paradigms can be a solution for fulfill the race towards future computing, but this new computing paradigm require new devices. And one of the most promising devices are memristive devices. So, a few words about memristive devices were briefly theorized in 1971 by Professor Leon Chua in the famous paper, The Missing Circuit Element, Memristor, that relates the existence of these components to symmetrical reasoning. But was only in 2008 that the group of Stanley Williams at HP Labs published the famous paper, The Missing Memristor Found, where the theoretical concept of memristor was associated to the physical mechanism of resistive switch. And in this case, ionics is coupled with electronics to form nano-ionic devices that were called memristive devices. Few words about the resistive switching mechanism. So these devices are very simple. So basically a metal insulating metal sandwich. Of course, in the IV plane, initially these are highly resistant because of the insulating nature of the insulator. If we apply a voltage, we can start the dissolution of few metal atoms to form ions that start to migrate across the insulating layer. If we further increase the voltage, this causes the accumulation of these ions and with consequent recrystallization to form again atoms on the opposite electrons. At a certain point, we have the formation of a complete channel that is connecting the two metal electrodes, and then a filament is formed. And so we are changing from a low slope in the IV plane to a high slope that is associated to a low resistance state. And this process is reversible, meaning that if we apply an opposite voltage, we can retract these atoms and we can reset our device. And so we can achieve the complete hysteretic loop that is the typical fingerprint of memristive devices. And so basically these devices are devices where the internal state of resistance depends on the history of applied voltage and current. And for this reason, these are promising for memory application as well as for analog computing and for the emulation of artificial synapses in the field of neuromorphic computing and artificial intelligence in general. So what is the main advantage of these devices? Well, it is possible by controlling the operational conditions to tune the internal resistance state with multi-level capabilities. So we don't have only 0 and 1 as in transistors, but we can have an analog behavior. So for example, we can tune the low resistance state in between more than 1 order of magnitude. This is something that we have demonstrated in a single nanowire devices, thanks to the controlling of the filament morphology that depends on how much current passed through the device. So we have an analog behavior in these devices. And if we think about real world, everything is working in an analog way, not in a digital way. And this is the key for exploring the power of computing towards the future computing paradigms. So to go towards analog computing and not digital computing. Well, we said that the memristive devices can emulate in somehow the synaptic plasticity in synapses. So, as probably all of you already know, the biological synapse is the building block of our brain and allows neurons to communicate. So, when an action potential reaches the axon terminal, so the terminal of one neuron that connects another neuron, this causes the opening of calcium channels that enter the axon terminal, and this causes the neurotransmitters to go through the synaptic cleft. And so these neurotransmitters diffuses across the synaptic clefts and binds the ligand gate ion channel on the postsynaptic membrane. And this is responsible for an increase of the communication in between the two synapses. The key aspect is that the synaptic way depends on the history of applied stimuli. And similarly, this happens in memristive devices. So if we have a metal-insulated metal structure, we can think about the metal line as a pre-neuron and the other metallic line as a post-neuron. And inside the insulating layer, depending on the history of applied stimuli, we can tune the morphology of the filament in an analog way. So if we applied voltage pulses that emulates the action potential of biological neuron, we can obtain a postsynaptic signal that is processed by the history of applied stimulation. So in some sense, the synaptic weight can be emulated by the memristive resistance. So this is an example of what we have done in a single nanowire devices. So without going into details, we can say that calcium ions play a key role. The influx and extrusion of this calcium inside the membrane of the biological synapse after that this synapse received an action potential is responsible for a change of the conductivity of the signal in between two neurons. And by emulating this process with silver ions, we can say that the field-assisted migration of silver ions can emulate the influx of calcium ions inside the biological synapse to form a silver filament that leads to an enhanced information transmission. And then we have a spontaneous physical-chemical dissolution of the filament that emulates the extrusion process of calcium dynamics. So just an example, if we apply a voltage to a device, a memristive device, we can have a gradual increase of conductivity. This emulates the influx of calcium ions. And then after the signal, the device spontaneously relaxes to the ground state, emulating the extrusion of the calcium. And the time constant of relaxation is about 20 milliseconds. That is a similar time scale of biological synapses. So just by properly tuning the operational condition, we can reach some analogy to biological synapses in memristive devices, also in terms of time scale of synaptic processes. And by exploiting this process, we can emulate some typical feature of synaptic plasticity, such as pair pulse facilitation. So what is pair pulse facilitation? So this is a rule in biological synapses that say that if two signals are temporally correlated, this will cause an enhanced transmission of signal. And this is an example. If we apply multiple temporal correlated pulses to a memristive device, we can see a gradual increase in the current that is related to a gradual increase of conductivity in an analog way. And of course, the time in between pulses that is related to the correlation of the input signal. So here we are two examples where we varied the waiting time in between pulses, so the temporal correlation determines this correlation, the change in the synaptic way. So if pulses are more correlated, this will cause a higher change of the synaptic strength, while if temporal pulses are less correlated, this will cause a less relevant change in the synaptic weight. And so basically we can emulate, this is what we have done in this paper, in collaboration with the Jülich Research Center. So we can emulate this, the influx and extrusion of calcium ions by using the migration of silver ions on nanowires that act as a memristive devices. So these are silver nano island of few nanometers on the surface of the zinc oxide nanowires that emulates the extrusion and influx of calcium ions and can give rise to the main feature of biological synapses that I showed before. So these are basically two terminal devices exactly as biological synapse. But anyway, this is only a single synapse. If we want to realize a brain, I would say, we have to realize networks of memristive devices as network of synaptic elements are composing our brain. So we can have basically two different approaches. The first approach is the top-down approach, where memristive devices are organized in regular cross-buy array networks. So the building blocks is the intersection in between the metal lines, and this is the insulating layer for the memristive devices. In this case, the behavior depends on single memory elements. So we have to address each single memory element independently to perform operations. But anyway, there is also another approach that is the one that we have pursued in the past. That is the bottom-up approach, where memristive networks can be realized through self-organization of nano-objects. And in this case, nanowires. So in this case, the building block is the intersection in between nanowires. In this case, differently from memristive network based on crossbar arrays, the players are not individual nano-objects, but their interaction that causes new functionality to emerge. So we have an emergent behavior that arises from complexity. And this is much more similar to what's happening in biological systems, but in this case, we need to develop new computing paradigms. And this is something that we have done in our paper. So you have also, if you are interested in that, we have shared completely our data set and also our codes that we have used to perform simulations that well matches the experimental results. So if you are interested, please visit these links. So all the codes, we usually share all codes in our lab, and so you can find on GitHub, and you can find on the paper the reference toward the GitHub. So if you are interested in that, please have a look and write me if you have some problems. But anyway, we realized a neuromorphic system by coupling self-organized network with crossbar arrays. So we take into advantage both memristive architecture to realize a neuromorphic system that take the input pattern, perform a spatio-temporal transformation of the input, and the nanowire network, this is a simulation, can evolve over time due to complex interaction between memristive system. So we have an emergent behavior that is able to spatio-temporal process the input signals. Then we have what we call the reservoir state, so the state of the network after the end of the input pattern, that is processed by a crossbar array of regular memristive devices to perform computation. And so we have realized a fully memristive architecture based on self-organizing nanowire networks coupled with crossbar arrays, taking into advantage both of the architectures. And so this is an example of how it works. So let's try to see if the video is working. Yes, so we use the NIST dataset as an example, but you can do also with other kind of dataset and basically with each kind of spatio-temporal input. So we have a pre-processing step where we binarize the inputs and we perform some adaptation to the network. Then we apply these pulses, voltage pulses. So white pixel means pulse, black pixel means no pulse, to different locations of the network. And then we have an emergent behavior. So the red intensity is proportional to the conductivity of one area of the nanowire network. And so we measure the output voltage at the end. So this is the final output voltage. This is a nonlinear transformation of the input signal. And we have one layer neural network that we have implemented in a crossbar arrays to perform classification. So in this case, we can do this all in hardware. And by taking into advantage the emergent behavior that arises from complexity in a nanowire network. And so just summarizing the activity based on nanowires. So the single nanowire devices were exploited in our lab as, I would say, memristive model systems to understand, because it turns out that these devices that are lateral devices can be exploited as a suitable platform for investigating ionic and electronic transport properties, as well as physicochemical phenomena occurring in nanowires. So the advantage is that we can also perform three-terminal measurement, because these are memristive devices, but this can act also as a transistor. So we can realize also MEM transistor based on single nanowells. So we use this to understand the role of metal oxide interfaces in these devices, as well as the role of environmental conditions, take into advantage that the filament is directly exposed. So you can also characterize the morphology of the filament in a quite easy way. And then also this acts as a memristive model system for investigating neuromorphic functionalities in single memristive devices, especially electrochemical metallization memories. And then we exploit the self-organizing nanowell network for unconventional computing. And it turns out that these networks, coupled with crossbar arrays, are suitable artificial neural network platform. And for this, with this kind of network, we perform pattern recognition, such as mixed dataset, but also speech recognition or time series prediction, such as Mackey glass time series prediction. And we are actually working for the implementation of other computing paradigms in this kind of networks by coupling this network with other crossbar arrays or by taking advantage of the spatio-temporal processing capability of these networks. And so I would like also to highlight that memristive devices have been considered promising for neuromorphic applications. And so there are a lot of groups working in this field. So have been shown to be able to process data similar to our brain by means of different computing paradigms and computer architectures, all involving the ability of programming the memristive devices in an analog way. But another feature of memristive devices is that they can show quantum effects in air at room temperature. So these are among few devices that can show effects from quantum mechanics at room temperature. So we are actually working in a joint project with other partners, including the University of Barcelona, the other national metrological institutes across Europe, the Jülich Research Center, IMEC in Belgium, that is trying to relate project results also with possible exploitation in industry to exploit these quantum effects in memristive devices. Just a few words about that. We wrote a review paper on this. We had an inside back cover on advanced materials recently on this topic, and this is a joint work from the project. And so if you think about quantized conductance effects in semiconductor devices, usually these have been obtained in the past to the constriction of a 2D electron gas that can be controlled by a gate voltage that represents a control variable. And these devices usually works at very low temperature, and the Fermi wavelength in this case is about hundreds of nanometers. So it's basically the constriction a mesoscopic object. But if we are dealing with atomic size metallic point contacts that are basically the conductive filaments that we can form inside our memristive devices, so if we are able to tune the morphology of memristive devices down to the atomic scale, we can achieve the Fermi wavelength that is about the atomic separation in metals. So the quantum point contact in this case has atomic scale dimension. And in this case, we can observe quantum conductance effects. And in this case, we can observe this at room temperature. But the main difficulties here is that we have to control at the atomic scale the distance in between atoms. And so in this review paper, we discussed how are the possible strategies to better control these quantum conductance effects in memristive devices. And we are actively working in this joint project for a wide range of application of these quantum conductance effects that I remind you that can be observed in air at room temperature. So this is quite unusual for devices to show quantum conductance effects at room temperature. And so I would like to acknowledge funding from this MEMQD project Memristive Devices is quantum standard for nanometrology. So if you are interested in these activities, so most of the results that I presented now are related to activities of this project that is that received funding from the MPO program, co-financed by the participating states, and from the European United Horizon 2020 Research and Innovation Program. And so if you are also interested in cooperation in activities of this project, such as measurement and so on, please visit our website or email me. And so these are my contacts. So feel free to write me or to follow me on the website or LinkedIn or something else. So thank you very much. I hope I gave you a short introduction, very short introduction of our main research activities. And of course, I'm open for questions, and I think the room is open for discussion. Thank you very much.
Thank you very much. Thank you. Thank you so much, Dr. Milano. So it was a wonderful presentation, and we understood many things, and we got clarified many methodologies that you have discussed. Now this session is open for question. I would like to request the senior scholar from this lab, Surojit, to kindly interact with Dr. Milano.
Thank you, Dr. Milano, for this wonderful talk. So now my small question is this, in this regard is, what is the forming voltage? Hello? Are you audible?
Yeah, I can hear you. Yeah.
So can you tell me about what is the forming voltage in this regard? In second or third slide, you have shown the INRiM characteristics. So in INRiM, what is the main thing that means forming voltage?
So I showed different devices. So the forming voltage strongly depends on the materials that you use, on the interfaces that you form, and mostly on the metals that you use. I would say for memristive device, I will give you an example. For memristive devices based on single nanowires, it's contacted by silver electrodes and platinum counter electrode, the forming voltage is usually lower than 10 volts. The target that we'll try to fulfill is to have all devices with the forming voltage below 10 volts. And this usually happens when you have a very close, when you use a very thin film. So reducing the thickness of the insulator can reduce the forming voltage, but of course will increase the leakage current. So you have to search for the best trade-off in between the two. And this depends strongly on the materials, but not only the materials, also on the peculiar characteristic of the material. So for example, if you do a silicon oxide thin film as a switching layer, if you do that by sputtering, or if you do that by electron beam deposition, these two thin film has a very different properties, even if at first sights can be similar, but and there you can have a strongly different forming voltages. But the idea is always to characterize materials and to try to optimize these materials, including the context of oxygen vacancies, the defectivity, and so on, to reduce the forming voltage below 10 volts. Even below 5 volts can be the best solution. But for single nanowires, we are not so interested in going below 10 volts because we use this as model systems. So we are not claiming to use this in architectures. So we would like to use nanowire networks for building neuromorphic systems, but the single nanowires based on metal oxide turns out to be very promising for gaining a deep insights into the physics. Then you can translate what you learned from single nanowire devices to other conventional memristive devices. I hope to clarify this.
Thank you. My another query is this: you have used the crossbar array structure to design some neuromorphic memristive device. So,
Yeah.
In that case, the main issue is that sneak path issue. That is a sneak current. So, how can you resolve this using this crossbar array?
So we have demonstrated a fully memristive implementation of this neuromorphic system in conjunction with Politecnico of Milano. So this was a jointly work with, I don't know if you know him, but Professor Daniele Iannini is quite famous in the neuromorphic community. And for this demonstration, we didn't use a full crossbar. For the experimental demonstration, we use a cross point, an array of cross points. So this should avoid any sneak current paths. But anyway, so for the proof of concept is the same, but of course the sneak current paths are a problem when you want to scale up this process. And this can be done through different programming strategies, such as applying minus the voltage divided by 2 on one side, and the voltage by changing the voltage polarity. So there are different schemes for programming and reading to get rid of these sneak current path issues. And the other important point is that you need both a selector device to properly select the cell to avoid this, or you have to engineering the interfaces. So meaning that if you realize a diode in between, you can select the memory cell, just avoiding the sneak current paths. Yeah, this is a problem when you scale up to large dimensions, of course. And there are entire research fields that's working actively on this. And I think that anyway, it's possible to realize this crossover array without any other active devices surrounding this. But this is surely a technological challenge, yes.
Okay, thank you for this.
Okay, thank you, Surajit. Now I would like to request Ripa, if you kindly interact with Dr. Milano.
I cannot hear you.
No. Yeah, good evening, Dr. Milano. Pardon me for my sore voice.
Maybe we are facing some technical issues. So, Dr. Milano, just give us some minute. We just
don't worry.
Take a look, whatever we have.
Don't worry.
Ritinabula?
Yeah, you are audible. You can carry on. You can mute your video.
Okay.
Yeah, now you can ask.
Dr. Milano, am I audible to you?
Yep.
Yeah, pardon me for my sore voice today. Actually, I have only one question. In fact, it's an inquiry. So, you in your lab, you are performing various simulations before you are actually performing the experiments. Am I right?
So it depends. It depends. We have different strategies. So in the case of single nanowires, we have performed simulation. After that, we have performed experimental results because we wanted to understand better by simulations what was going on inside the device. But the case of single nanowires is the case of a model system. So we are more interested in the physics behind. Okay, so we use a kind of modeling in collaboration with the University of Barcelona that is more devoted to understanding the physics. For example, the Schottky barriers that are playing the role in memristive devices, the migration of ions, and so on. For nanowire networks, we are using a different approach, completely different approach. So we start by simulations. If you want to implement a computing paradigm, you have to start by simulation, because experiments, it's already very difficult and time consuming. So you have to start with a computing platform that you are confident that will work. So what we did is to characterize in depth the single nanowire network, and then try to build a model that should be as simple as possible of that is catching main feature of the nanowire networks. Then use this model that can be also a simplified model, but should be not so computer intensive. Then you can use this model for try to implement different strategies of computing. Then you select the best strategy and you try to do the experiment. Yeah. In this way, the simulation can help you to save time and, of course, also money, because you have to perform several steps for the fabrication and so on. So what we do is actually try in simulation to perform computing and then to move to hardware. And we are trying also to increase the model, the capability of the model to be able to describe main features of these devices that are multi-terminal devices in case of nanowire networks. So it's more difficult than a single device. So you have to use the graph theory. I don't know if you are confident with the graph theory, but you have to use this mathematical framework to perform computation, to solve the Kirchhoff laws, and to see the evolution over time. And so you can understand the capability of the network to perform spatiotemporal processing of your inputs. And for example, just also placing the electrons in the right position is an issue. And so you have to perform simulation before doing the hardware, of course. And in principle, this is the same approach that all the neuromorphic computing is actually performing. So starting from a single device, from a model, then modeling the architecture, and then implementing the architecture in hardware. I hope to
yeah, I got that. Yeah, thank you. So actually, is there any specific software or programming that you are using for that simulation, or is it your own?
Yeah, so for simulation about the physics, I would say for single nanowires, the models are mainly developed by University of Barcelona by taking into account our experimental results. So we continuously interact to work toward that. And in this case, the models are in SPICE simulators. But for the nanowire networks, we started from scratch by using Python. And we saw that it's the best solution also for sharing the code and for adding the code and for implementing this graph theory inside the software. So we are now working actively on Python for the realization of architectures, while SPICE is also used for modeling single devices, for behavioral modeling, we say.
Yeah, thank you. Actually, another question I have is, can you utilize Gaussian for the molecular modeling if you are using a certain molecule for the neuromorphic computing?
So you mean, if I understood correctly, you mean molecular simulations, if this can be helpful, right?
Yeah.
Yes, we did in the framework of quantum effects in memristive devices. We are actually collaborating with a group that perform molecular dynamics and DFT simulations. And these kind of simulations are more important when you want to deal with the physics of your devices. And the main advantage is that you can gain insights about the molecular structure of your filament, but the main drawback is that you need a very long time to perform this kind of simulation. So usually you have to restrict to a very simple model. So, but yes, in principle, yes, to understand the evolution of the filament, molecular dynamics is for sure a good idea.
Yeah, thank you. It was a very nice presentation and I learned a lot of new things. Thank you.
Thanks to you.
So thank you, Rahul, for your kind interaction. And actually, this is the advantage of such kind of interaction. When we seek to know many things from you, we come to know many things we don't know. So now I would like to request Farhana to kindly interact with Milano.
Hello.
Hello. I cannot hear you. Probably you are muted.
Hello. May I audible?
Yeah.
Okay. Thank you, Dr. Milano, for your wonderful, presentation, and myself, Yasmin from Thin Film and Nanoscience Lab. So I would like to say that it was such a wonderful experience attending your precious lecture. So since we are working, just hold a second. Okay. Since we are working in the field of resistive switching and expecting that we can work in a fruitful collaboration in the near future, and I hope your knowledge in the field of resistive switching along with neuromorphic computing will direct us for the future device application and all. Thank you so much.
Thank you very much. Yeah, I also hope that this can give rise to new ideas in this neuromorphic community. Thank you.
So thank you, Farhana. So it was a wonderful compliment. So right now we have with us Professor Hussain. So sir, if you want to interact with Dr. Milano.
Yeah, so thank you very much, Dr. Milano.
Thank you. Thank you for the invitation. I cannot hear you. Anymore.
Ashad sir, your voice is not coming.
Yeah, but I cannot hear Professor Hussain.
Maybe you have some technical issues, sir. Just wait a minute, Dr. Milano.
Yeah, don't worry.
I think some technical issues are there from our end only. So that's why we are facing some issues. So meanwhile, Dr. Milano, I want to ask a few things. The materials you have chosen for this construction of memristive devices, so how much hope you have other than these oxide materials can lead this field also?
So if you understood correctly, so if we have ideas about other materials, right?
Yeah.
I think for the realization of electrochemical memristic cells, metal oxide are the best. Because you can control easily the composition, the stoichiometry, and so on. What we are moving now is towards nanowire networks that are basically metallic nanowires, where core shell nanowires, where we have a core that is metallic and a shell of 1-2 nanometer that is a polymer. And this is also promising because it can slow down both the operating voltages, the form voltage, and the set voltage. So basically, I think that both metal oxide as well as maybe also polymers, but for particular applications, can be good ideas. But the most important part, I think, is to choose properly the electrodes. So the electrode materials, for example, if you choose silver, the ionic mobility of silver is quite high, so you can move these atoms quite easily. And so this is a good choice if you want to perform spatiotemporal dynamics in the temporal scale of milliseconds. But also copper can work. It strongly depends on your application, I would say. But yeah, I think that exploring different oxides, we are currently working also on niobium oxide for different applications. There is a PhD student that is working actively on that. Can be promising. So for all oxide, for the combination of oxide and materials, but most of all, for all the combination of interfaces. So interfaces are even more important than the material itself. Because if you're dealing with thin films of 10 nanometers, the interface properties are more relevant than the bulk properties of your oxide. So you have to choose the right combination between metals and metal oxide to properly engineering the interfaces. This is something that we are demonstrating in a single nanowire about in the work that we have discussed before. So the experimental and modeling of metal-metal insulator interfaces for that. Yeah.
So thank you. So as I can see, Professor Hussain is connected through HOD. Professor Hussain, can you hear me? Professor Hussain? Sir, you are there, sir?
I cannot hear you, maybe.
Yeah, it's maybe the connectivity issue, Dr. Milano, we are having.
Yeah.
So actually, you know, such kind of internet, that e-conferences we are having.
Yeah,
so
yeah.
These are totally dependent on technological issues.
Yeah. I know.
So meanwhile, I can see Dr. Joshimuddin is also with us. Dr. Joshimuddin is from Human Physiology Department. So he's a guide, a path guide to us. So Dr. Joshimuddin, would you like to interact with Dr. Milano?
Thank you, Ridhanova. And thank you, Dr. Milano, for a nice presentation.
Thank you.
No, I have no such question. I have a query, a small query to Dr. Milano. In biological synapse, there is a specific voltage or action potential is necessary to break the synaptic cleft to release the calcium. What voltage you are giving in your devices to break the barriers between the conductive and non-conductive layers?
So yeah, in biological synapses, if I'm not wrong, we are dealing about millivolts, few millivolts, tens of millivolts.
Yes.
We are working in our devices currently with hundreds of millivolts. So not so far away. So there is still possibility to improve by properly engineering materials that are involved in the interfaces to further lowering these voltages. Yes. But I think that reaching the same voltages that are used in synapses can be quite difficult because we need some voltage for the dissolution of ions, so the dissolution of atoms to form ions. So this is the physical limit that we can reach.
Oh, thank you. Thank you, Dr. Milano.
Thank you.
So thank you, Dr. Joshimuddin. It is always nice to have you with us from every perspective. So, so due to the connectivity issue, we lost Professor Hussain. So right now he is with us. Professor Hussain, can you listen to me?
Yes.
Okay. Sir, yeah.
So sorry for the technical problem. Actually, I just would like to congratulate Dr. Milano and also to thank Dr. Milano for his nice presentations. Though we are working on resistive switching, but neuromorphic computation yet we didn't started. So maybe in near future we can plan. And also, Dr. Milano can guide and help us if we have and our students can think about, say, regarding simulation and other computation kind of things, so that we can have idea about the our devices before experimental study. So in this respect, I request Dr. Minalu to kindly extend his cooperation in near future. And also, I see from literature, neuromorphic computation, mainly such devices are very effective, which responds taking data from the environment, and people are planning so that this may be a good kind of thing, so that it will sense the body conditions and can be used for drug delivery kind of thing, and also in artificial intelligence also. So I would be happy to just have a comment from you if really in near future whether this will be physically possible.
Oh, well, that's a good question. I would say for the really next future, what I see is the application in memory computing of such kind of ordered crossbar arrays of Memristive devices. I think this will be possible in the near future also because there is a huge interest now from different startups all across the world that are developing their own arrays of devices and so on. For this means in memory computing means basically matrix vector multiplication that can be done in one shot in Memristive devices, in arrays of Memristive devices. Then what I will see for the future is the use of Memristive devices for really unconventional computing paradigms, like, for example, reservoir computing. So we wrote now a paper on that, that by exploiting the self-organized nanowire networks, you can implement reservoir computing that is a kind of physical computation, so performed in hardware, that basically reduce the training procedure that you require for the neural network. So as you know, probably most of the power required for the neural networks belongs to the training part. And usually training a neural network in software is quite long because our hardware is not optimized for that. But by using unconventional computing paradigms, so reservoir computing is only one of these computing paradigms, so exploring different computing ideas in different devices can be really disruptive in this research field. So the important part is not to think about using the same computing framework in this device architecture that is completely different. So if we really want to take the full advantage of using Memristive device, we have to rethink again the way we are performing computing. And so in this way, this technology can be disruptive. Otherwise, if we want to apply some conventional computing paradigms in Memristive devices, maybe this will not be so convenient. Okay, so this is my personal idea, of course. So difficult to say, but for the next future, I see memory computing platform and also the Memristive devices as storage platforms.
Yeah.
So yeah, it's maybe we are optimistic. Then there will be some good applications. Okay, so our students, they are employing some biomaterial as well as plant extract kind of thing to design some biocompatible devices so that it can resolve or help to minimize the EWAST kind of issues. So and they are designed some ROM as well as bipolar RAM kind of devices. So can you comment or guide how they apply the simulation or idea about their performance of the device using computations?
Yeah, so you mean you have devices, you have a model of the device, you would like to implement computation,
Yeah,
if I
yeah.
understood. Well, first of all, you have to decide the computing framework that you would like to have. So depends if your devices shows stability over time or if you have short-term memory. So this is the big difference. So if you can potentiate and depress the single synapse, you can use some computing paradigms such as so that are basically in memory computing. Otherwise, if your devices are not stable over time and you have short-term memory, you have to deal with temporal dependent computing paradigms. So this is, I think, the first choice. Then you have to develop a model, a simple model for your device, and then you can play with an array of model devices to try to implement this some computing. I think that's the best strategy. Then when you are sure that you can do computing, you can realize these arrays in hardware.
And in this regard, can we have your cooperation or I mean support, or can you help us in this regard? Is it possible?
Yeah. If you need some help, just please write me or yeah.
Then what our students can do, they can we will communicate with you regarding our result as well as device also, because recently we designed one device using some protein, and we found that it's physically stable up to 700, more than 700 days. So it would be because stability of biomaterial is a concern sometimes. So it will be good if we apply some modeling and can predict about the this kind of thing. We did some extrapolations, but modeling would be a good, I mean, better one. So we may communicate with you, and if you can help us, then we can collaborate in this regard.
Yeah, for sure. I think the first step, if you have a memristive devices, is to be sure that effectively you have memristive devices. So there are a lot of errors in literature, I think, dealing with memristive devices that are not truly memristive devices. So you have not, as a first point, you have to demonstrate that your devices is a memristive device, is not only a capacitor. Because sometimes when you apply voltage pulses, for example, to a device, you can charge and discharge your capacitance, and basically you can confuse this with memristive devices. So first of all, you have to have a solid characterization of your devices, showing that these are effectively memristive devices. Then, when you have such kind of measurement that include IV sweeps over time, then you stop at different memory levels and you see that these are stable over time. So this is something that should be done before. Otherwise, I think it is questionable if these are memristive devices or not. Of course, I don't know, of course, the characterization that you have done, but I think this at least should be done. And then you have to characterize the endurance properties and the retention properties of these devices. So how many cycles you can have, how these resistance states are stable over time. So you can do that for different resistance states on the same device. And then you have to evaluate the device-to-device variability. The device-to-device variability is fundamental if you want to implement some computing, because a lot of works characterize only one device, then develop one model for one device, and saying, okay, we can scale down, we can scale up this with thousands and thousands of devices. But the question is, are you able to do the same device thousands of times? The answer usually is not, unfortunately, but you can do that with a range of variability. And if you want to do computing, you have to take into account the variability that you have, device-to-device variability. So evaluating this with measurement can strongly help you also in understanding which is the best computing strategy. Okay. So I think this should be done from the beginning. So, but this is, of course, only my opinion. So there are, of course, different views on this. But I think, first of all, being sure that you have a memristive device. Second, try to evaluate all the key aspects, key feature of memristive devices, then including also device-to-device variability, and then developing a model of the device. That can be also easy, simple.
Okay. Actually, our students, they are doing this device to device means we study the device yield. So we design number of devices, then check how many devices can give reproducible data. So this is there, and also they study retention behavior also, and this cyclability also. So this kind of study we are doing. So maybe we can share some of our informations and have your guidelines. And recently, one of our students, he is trying to learn something using Gaussian. We have a software, so maybe using this also, or maybe what you suggested. If we have your guidance, or you can help us. So in this way, we can collaborate and proceed further. And hopefully, we'll have some fruitful collaboration in near future. And our student will find some new idea and space also for collaborations. So thank you very much, Dr. Milano, and hope the interaction will continue. Thank you very much.
Yeah, of course, just write me, or as I told you before, we usually share all our codes and our implementations in our papers. So if you have a look to our papers, you can find most of the information, practical information that usually are good for students. But of course, you can write me anytime you want. So you can, if you want to share some data, I can share my ideas as you want. For sure, I'm open to collaborate. Okay.
Sure, we will do it. We will do it. And in near future, I would be happy if you visit India or also in my level. So we do organize internal conference sometimes. So next time when we do organize, definitely we will invite you. Thank you very much.
Thank you. Thank you very much. Thank you for the invitation, and it's always good to share ideas, and I think that's very important. So thank you again.
Okay, bye.
Okay.
So thank you, Professor Hussain, and also Dr. Milano, and hopefully we'll have a fruitful coordination with us. Okay, so we have with us some of our master students. They must have understood and they must have learned many things. Maybe not all things, but maybe many things. So if any one of you want to interact with Dr. Milano, so he's open for you. Any master students?
Good evening, Dr. Milano. That was a very nice talk. I am Subhuti from Tripura University, and I am doing my master degree. I have a very little question about what is Memristive device. Can you explain briefly, please?
So, in order to, so you would like to know how to be sure that a device is a memristive device. So, if I understood correctly. So, the first thing that you should see is the hysteretic loop in the IV plane, and this should pass through 0. Otherwise, it's not a memristive device, but it is a capacitor. Memristive device means that if you are in a state and you stop there, this state is stable over time, at least for a certain time scale. So, in order to characterize this, you can start with IV sweeps to see the hysteretic loop in the IV plane. If this is passing from 0, you are confident that this should be not only a capacitance, but then you can also try to see if the state is preserved over time, and if you have then this can be stable over time or not. So this does not. This depends on the memristive device that you have, because there are a lot of memristive devices with short-term plasticity. So you stop in a state, and then they spontaneously relax to the ground state. But you have just to be sure that these are memristive devices. This can have an hysteretic loop in the IV plane, and this should pass through 0. I think this is the best, I will say, definition. Then the definition is not exactly the definition given by Leon-Chua in 1971, but this is a theoretical memristor. We are dealing with memristive devices that it's always better not to call them memristor, but memristive devices, because Leon-Chua decided to enlarge a little bit the definition through all the devices, or the history on the internal history of the resistance depends on the history of applied voltage and current. So basically, all devices that show a dependence on the history of applied voltage and current can be called memristor somehow.
Okay, so thank you. Thank you, Subhrajyoti.
Hello.
Oh, maybe someone is there. Okay, you can speak.
Hello.
Yes, sir. Hello.
I cannot hear you very well.
Hello.
Yeah, now I can hear you.
Okay. Hello. Milano, I'm Rajdeep Sharma. I'm also a student of Masters in this university. My question was to you about, like, how did you choose that you want to do research on thin films and nanoscience? And how did you out what students are equivalent here to?
Sorry, I didn't get the point because your voice was not so stable. Can you repeat, please?
Okay, hear me now?
Yeah, more or less. Not very well. If you want, you can write on the chat also.
Hello, can you hear me now, Dr. Milano?
Yeah.
Okay, my question, I'm Rajdeep Sharma of this university. I'm doing my master's. So my question was to you, it's about your, how did you choose your this field as your research career? Like, how did you find out while you're a student that I want to do nanoscience and I want to become a physicist on this field, on this subfield of physics?
So, as sometimes this happened, this was completely by chance. But I would say I did my master thesis working on graphene materials. So in the characterization and growth of materials based on 2D materials such as graphene. Then I was looking for a PhD in the field of nanoscience, because I like this kind of topic. But at the end, I wanted also to search for a topic that was highly interdisciplinary, dealing with not only, I would say, nanoscience, but also with a lot of physics, a lot of material science, a little bit of chemistry, and why not also a little bit of biology. And so it turns out that Memristive Devices was the perfect conjunction in between all these fields. And so I was interested in both modeling and experimental activities. And so with Memristive Devices, that there is room for collaborate also with people outside this research field. So people working from chemistry or material science or biology or medications, and so on. So basically, I decided to work on that because this was a highly interdisciplinary field that allowed me to collaborate with a wide range of different fields. That's why I decided to work on that. And then it is opened also the possibility to work both on experimental and theoretical side. That was something that I was interested to, and also mathematical modeling. And so that's why basically I went into this research topic, and I did my PhD there in this research topic, and then I continued moving to another institution, but working still on Memristive Devices, yes.
So thank you. Thank you for the students, as you have understood. So since we are having master students right now watching this presentation, so let's say they have lots of ground level questions, not maybe technical, but it is maybe career oriented. So they pursued their questions to you. So
yeah, that's good.
That's good. Yeah. So maybe students may directly email to Dr. Milano also if you want to know many things, whatever it is. It may be technical, it may be not technical, but you may email to Dr. Milano. He will be open for you. Is that okay, Dr. Milano?
Yeah, for sure. I'm open for replying to emails, and if you have curiosity on details from our work or something else, it's okay. Fully okay.
Okay, so with this note, I am winding up this session with the permission from Professor S.A. Hussain, the HOD, Department of Physics, Tripura University. Also, we had with us Professor R.K. Nath. As I can see, Professor Nath, you are there? Okay, maybe we have lost him in this connection. So thank you, Dr. Milano, for agreeing to give your presentation in this platform. And we are very happy to have you. Please do visit us. And we also arrange some kind of international conferences periodically. We'll invite you if it's possible and convenient for you. Please do visit us. Our hearts are always open for researchers like you.
Thank you very much for your invitation, and hoping for also good collaborations. And thank you very much again.
Okay, so we'll have our conversations continue. And with this note, I'm winding up this session. Thank you very much. Tata.
Thank you.
Bye.
Bye.